So Laplace equation in two-dimensional. Most suitable solution. What is the most suitable solution? Now discuss here. Laplace differential equation is del u del x square plus del u del y square equal to 0. This equation number 1 is called a Laplace equation in two-dimensional. What is the most suitable general solution will be depend on the boundary condition on the problems. The boundary condition first your type of first. If first is if ux y equal to 0 as y tending to infinity, means y tending means here which is tending to infinite according to y axis, and x in 0 to a, x is here 0 to 0 and here coordinate of a0, so x lie between 0 to a, then that case the most suitable general solution is uxy equal to c1 cos lambda x plus c2 sin lambda x, c3 e raised to lambda y plus c4 e raised to minus lambda y. So for above boundary conditions, first here y equal to 0, then ux equal to 0, ux 0 equal to f of x, then according on the x-axis, that is the initial. Here x equal to a, the u a y equal to 0, that is the u a y equal to 0 here, and third here x equal to 0, so u 0 y, u 0 y equal to 0, and here y ux y equal to 0, y equal to infinity, or ux infinity equal to 0, this is ux infinity equal to 0. If u equal to xy as y equal to b, it means which is bounded, it means not tending to infinity for x in 0 to a, then the most suitable solution, reduce equation 2 we get, the equation 2 reduce we get, so equation 2 reduce ux y equal to c1 cos lambda x, c2 sin lambda x, and second term reduces c3 cos h lambda y, this is a hyperbolic function, and which is c4 sin h lambda y is 3. This is the most suitable solution. Boundary condition u0 y equal to 0, here u0 y 0 y equal to 0 y, means here that is boundary condition u a y equal to 0, u y equal to 0, ux b equal to 0, ux b here, that is which is not tending to infinity, that is a given condition, is a boundary insulated, that is insulated, so ux 0 and ux 0 equal to f of x, or boundary conditions u0 y equal to 0, ux 0 equal to 0, u a y equal to 0, or ux b equal to f of x, here ux b equal to ux b equal to f of x, and ux 0 equal to 0, and x equal to, which is the insulated plate, means here bond is fixed, it is a here is fixed, and or another case you can say this function of x is given, and u is not tending to infinite, that is suppose not y equal to b, there is any other boundary condition given in form of this del u del x equal to at x equal to a, del u del y x equal to b, and so on. So that case thus most suitable taken is equation number 3, that case taken equation number 3. Boundary condition is type of 2. If ux y equal to 0 as x tending to infinity and y in 0 to b, means here x tending to infinity, that is the x diagonal, which is x axis and which is y axis. So the most suitable solution is ux y equal to c1 cos lambda y, c2 sin lambda y, c3 e raised to lambda x plus c4 e raised to minus lambda x, or ux y c1 cos lambda y plus c2 sin lambda y, c3 cos h hyperbolic lambda x, and c4 sin h lambda x. That equation which is reduced to, then we get this. Boundary condition for equations 4, ux0, ux infinity is 1. It means ux infinity means that case here is the x tending to infinity. Then we get this ux b equal to 0 and u0 y equal to f of y. And for b, here second, if ux y 0 has x equal to a for y in 0 to b, 0 x equal to a means which is not tending to infinity. It means only this insulated plate. Is the boundary condition means fix, which is the fix. That case here we get the most suitable solution in 5. If x does not tending to infinite, then most suitable general solution is 5. Ux y equal to c1 cos lambda x plus c2 sin lambda y, c3 cos h lambda x plus c4 sin h lambda x. So Laplace differential equation problem. So first we take care most general most suitable solution, after then find out solutions. Thank you. So Laplace equation is first problem taken, solve del t del x square del t del y square equal to 0 subject to boundary condition. Here first boundary condition ux y equal to 0 as y tending to infinity, means ux to infinity equal to 0, u0 y equal to 0, u pi y equal to 0, and x0 equal to sin x. Here boundary condition define according to x axis, which is y axis. Here y tending to infinity, x0 is 0 infinity, y equal to 0, x0 equal to sin x, and here that is this is coordinate pi 0 and which is 0 0, that is here x equal to pi, so pi y equal to 0 and y x equal to 0, y equal to 0. So solution Laplace equation del 2 del x del 2 del y square equal to 0. Most that conditions here y tending to infinity, that case the most suitable general solution is uxy equal to c1 cos lambda x, c2 sin lambda x, c3 raised to lambda y, c4 raised to minus lambda y. This is equation number 2. Now apply the boundary conditions. First ux infinity equal to 0, we get c3 equal to 0. Put x y is equal to infinity, here 1 upon, so which is not equal to 0 first, which is not equal to 0, but which is we get 0, 1 by c4 upon infinity we get 0, and we get here remaining term c3, so c3 becomes 0. Putting equation 2 becomes putting the value of c3 in 2, so we get uxy c1 cos lambda c2 sin lambda x, c4 raised to minus lambda y. Again apply the boundary conditions, u0 y equal to 0 means putting x equal to 0 here, so c1 cos 0, c2 sin 0 e raised to minus lambda y becomes c1 equal to 0. Again equation 3 becomes putting the value of c1 equal to 0, xy c2 sin lambda x dot e raised to lambda y, xy c2 c4 sin lambda x e raised to minus lambda y. This is equation number 4. By condition again u pi y equal to 0. Now using 4, here c2 c4 sin lambda pi e raised to minus lambda y equal to 0. So c2 c4 e raised to minus lambda y not equal to 0, sin lambda pi equal to 0, sin n pi, lambda is equal to n. So from 4, putting the value of lambda, uxy you get c2 c4 sin n pi e raised to minus n y. Now unx, find unxy bn sin nx e raised to minus ny. Bn is equal to c2 c4 here. uxy equal to 1 to infinity bn sin nx e raised to minus ny, where bn equal to 2 upon a 0 to fx sin n pi x upon a dx. Now which is consider equation number, no equations. Expand equation 5, we get uxy, they put n equal to 1, we get the first term here, second terms putting n equal to 2 and so on. And first given ux0 equal to b1 sin x, b2 sin 2x and dot dot 7. is up to infinite. Question number 7. If always consider if our uxy in given ux0 in given in form of sine, so directly you can expand the equation 5 and find out compare and find the value of b1 b2 and so on. So it is required, then solve. So don't write or don't evaluate bn, that formula. This is an easy process. If evaluate bn, this so lengthy process. So if always remember, if ux0 is given sine format, sine x, sine 2a, sine qa, so then expand 5 and compare. So ux0 is here in that problem. ux0 equal to given sine x, that is equation number 8. Using 7 8, sine x equal to bn sine x, b2 sine 2x is equation number 9. Equating the coefficient of the like term on both sides of 9, we get b1 equal to 1. Here like term means sine x, coefficient of sine x, coefficient of sine 2x and so on. b1 equal to 0, b1 equal to 1 and bn equal to 0 for n is greater than 2. Now putting the value of b1 in 6 here, and we get uxy equal to sine 6 here 1 and sine e raised to minus y, that is here sinus e raised to minus y, which is required solution. Problem of Laplace partial differential equations. Now solve the equation del du del x square del tu del y square equal to 0 with the conditions. First condition, u equal to 0 when y tending to infinity for all x, that is u x infinity equal to 0, u equal to 0 when x equal to 0 for all y, so u0 y equal to 0. Second boundary condition, u equal to 0 and when x equal to 10 for all y, that is u 10 y equal to 0, and u equal to k 1 minus x when y equal to 0 for 0 less than x less than 10. This it means here ux0 equal to f of x, that is k 1 minus x is given. So Laplace differential equation del tu del x square del tu del y square equal to 0. So now here first according to x-axis is work going on, that is here x, and here this is y tending to infinity. Now here ux infinity equal to 0, x infinity, and here this is according to y, so that is x equal to 0. Now u0 y equal to 0 is the boundary here, and here x is equal to 10, that is here which is x equal to 10. So now u 10 y equal to 0 here, and y equal to 0, x0 equal to f of x. Since u tending to infinity as y tending u tending to 0 as y tending to infinity, so that boundary conditions, most suitable general solution of one is now uxt equal to c1 cos lambda x, c2 sin lambda x, c3 e raised to lambda y and plus c4 minus lambda y. This is equation number 2. So now apply the boundary conditions. 1 ux infinity equal to 0. Now equation 2 becomes, so which is at it is c1 cos lambda plus c2 sin lambda x and c3 e raised to lambda y plus is c4 upon e raised to lambda y. Now put the value of y infinity, so we get that term 0. Simplify this and we get here c3 equal to 0. The first constant in c3 is 0. Now c3 0, so equation 2 becomes, put c3 equal to 0 here, so we get uxy is equal to c1 cos lambda x plus c2 sin lambda x and c4 e raised to minus lambda y. So now apply boundary condition u0 y equal to 0, putting x equal to 0 in 3 here above, so we get 0 here, c1 cos 0, c2 sin 0 and c4 e raised to minus lambda y. So now becomes c1 equal to 0 and that term not equal to 0. Now equation 3 becomes, again put c1 equal to 0, so equation 3 becomes uxy c2 c4 sin lambda x and e raised to minus lambda y. This is equation number 4. Now apply the boundary conditions. Third, u tan y equal to 0. The c2 c4 sin 10 lambda, here put, and e raised to minus lambda y equal to 0. The sin 10 lambda equal to 0, so sin lambda pi equal sin n pi, so lambda is equal to n pi upon 10. Putting the value of lambda in 4, here 4, and we get xy c2 c4 as it is, and in place of lambda n pi upon 10 x e raised to minus n pi by 10 y. Now vn xt bn sin n pi x upon 10 and e raised to minus n pi upon 10 y. And now uxy, that is here uxy equal to 1 to infinity un xy. So xy 1 to infinity bn sin n pi x upon 10 e raised to minus n pi upon 10 y. This is equation number 5. Now we get here ux0, find out 1 to infinity bn sin n pi x upon 10 e raised to 0 is 1. So which is the Fourier half range sine series, and bn is equal to 2 upon a 0 to f of x sin n pi x upon a dx. On comparing to given bounding conditions, find out the value of a. The a is equal to 10, fx equal to x0 equal to k1 minus x given. Now bn here 2 upon 10, 0 to 10, k1 minus x sin n pi x upon 10 dx. So now k by 5, here k is the constant, so k by 5 0 to t1 minus x sin n pi x upon 10 dx. So now here apply the Leibniz theorem. U v dx is u v1 minus u dash v2 plus u double dash v3 and so on. What is the number of required? So v1 means here ant of v, v2 ant of v1, similar and so on, and u dash is your differentiation of u double dash differentiation of u dash and so on. So now here apply first function into derivative, first function into the integration of second. Integration of sine is minus cos n pi x upon 10 divided by n pi upon 10. So into u dash, here 1 minus x in differentiation, so minus 1. Again u into v2 means integration of, that is here v1. Integration of v1 is here cos, integration of cos n pi x is minus sin n pi x 10 minus and divided by n pi upon 10, or before here present n pi upon 10, so we get n square pi square upon hundreds. Now 0 to 10. Apply upper and lower limits. So put at 10 x equal to 10, here 1 minus 10, that we get 9 minus 9, or here minus 9, so plus 10 upon n pi cos n pi, again here minus plus, here minus, so 100 upon n square pi square sin n pi. Minus lower limit, minus here minus 1 0 is minus, when we get here minus 10 upon n pi cos 0 minus 100 n square pi square sin 0. So we get 90 upon n pi minus 1 raised to n, that is which is minus 1 raised to n. So we get this, and cos sin n pi, that is just sin n pi equal to 0. So second term 0, minus plus, here plus 10 n pi, and so now 10 common, 10 here common, so 5 2 is 10, so now we get 2k, and 1 plus, that is here 1 plus 9 into minus 1 raised to n upon n pi. Now putting the value of bn in 5, we get, so 5 here bn, so now putting the value of, so 2k, 1 plus minus, no, plus 1 plus 9 into 1 minus 1 raised to n pi sin n pi x, here n pi x upon n pi x upon 10 e raised to minus n pi y upon 10. Now 2k is the constant, 1 to infinity summation of 1 plus 9 into 1 minus 1 raised to n pi sin n pi x upon 10 e raised to minus n pi y upon 10, which is final answer.